This is Reuben Gerlitz, Chief Engineer of the Propeller Division of Robbins and Meyers. This recording, in combination with the illustrations of the accompanying Design News article, will demonstrate the value of octave band analysis in measuring fan noise. It will also provide a better understanding of the effect of various noise control methods. The octave band analysis of a typical propeller fan is shown in Figure 2. The following series of sounds presents the same data in audio form. First, the overall noise. Now, octave band number 1. Number 2. 3. 4. 5. 6. 7. 8. And again overall. The noise levels of octaves 5, 6, and 7 are of particular significance, since these bands carry most of the content of speech. This will be demonstrated by making an octave band analysis of my voice as I read something unfamiliar.
First, the overall.
The behavior of sound energy.
1. 2. 3. 4.
Becomes distributed over an increasingly larger surface area.
5.
And sound intensity decreases in accordance with the inverse square law.
6.
The total sound power is equal to all of the sound energy
7.
to the surface of an imaginary sphere surrounding the sound.
8.
Expressed in decibels, this is known as power level. The word level indicates
Overall.
That a reference power is implied. Figure 3 shows the octave band analyses of two fans, equal in overall sound pressure level, but different in the distribution of their sound energy over the spectrum. Fan B with lower levels in the higher octaves is quieter. This is fan A. Fan B. Note also the greater interference with speech communication by fan A as I read.
Without fans.
Specifically, this article deals with fans,
Fan A.
but it also happens to go to other noises as long as the noises are similar to one another.
Fan B.
The equations and charts given are mathematically rigorous for individual octave bands
Without fans.
and for overall sounds with similar spectrums. Figure 5 shows the influence of room constant on fan noise. Note the difference in noise spectrum for fan A when placed in a small room and then a large room. Microphone to fan distance is the same in both cases. First, the sound in the small room. And now in the large room. The effectiveness of barriers is shown in Figure 6. The microphone is located 10 feet from the fan with a barrier midway between them. First you will hear the fan directly without a barrier, then with a porous fiberglass barrier, then with an impervious plasterboard barrier. Finally, the microphone is moved closer to the plasterboard barrier, deeper into the shadow zone. First the fan without a barrier, with a porous barrier, with an impervious barrier, and microphone in shadow. Figure 7 shows the effect of duct lining with and without baffling. Note the greater attenuation at higher frequencies, which provides desirable benefits in reducing interference with speech. This will be demonstrated by changing ducts as I continue to speak at a uniform level. The demonstration will begin with the fan operating in an unlined duct. As the commentary continues uninterrupted, we will subsequently switch to a straight line duct and finally to a line duct with baffles. Attenuation may also be introduced to consider for X-ray construction, which increases perimeter area ratio. In a line straight duct, attenuation is proportional to the perimeter of the lining and inversely proportional to the cross-sectional area. Zigzag baffles increase attenuation by providing additional absorption with multiple reflection. The relative loudness approach outlined in this article has considerable merit in handling noise control problems. The linear nature of the relative loudness unit, the SONE, makes it easy to visualize the meaning of noise loudness ratings. Furthermore, the various formulas and charts give one a feel for predicting results. These predictions can be just as accurate as with the more complex decibel approach.